Pick up your phone. Look at the screen. That glossy little rectangle you hold in your hand contains a holographic sticker, probably on a credit card in your wallet, or the security seal on a package you received last week. Tilt it in the light. Watch the image shift. A three-dimensional dove, a shimmering logo, an iridescent pattern that seems to float above the flat surface. Now hold that thought. Because what if I told you that everything you see right now, the walls of the room you are in, the chair beneath you, the body you inhabit, the stars wheeling overhead through the atmosphere, might work the same way? What if the depth you perceive, the volume you move through, the three-dimensional space that seems so solid and so real, is nothing more than a projection? An impossibly complex hologram emerging from information written on a distant, two-dimensional surface. This is not science fiction. This is one of the most profound and carefully considered ideas in modern theoretical physics. It has a name, the Holographic Principle. And if it is true, then you and I and everything we have ever known might be living on the surface of a cosmic boundary, perhaps even the event horizon of something very much like a black hole. The story begins not with holograms, but with entropy, not with surfaces, but with the deepest interiors physics can describe, not with two dimensions, but with questions about information that go back to the foundations of thermodynamics itself. Let us begin where all truly strange ideas in physics begin, with someone who dared to ask an uncomfortable question. Someone who looked at the equations, noticed something that did not add up, and refused to look away. The year was 1972. The place, Princeton University. A young doctoral student named Jacob Bekenstein was wrestling with a paradox that had been quietly troubling physicists for years, though most preferred not to think about it too hard. The paradox concerned black holes and entropy. To understand why this matters, you need to understand what entropy is. In the simplest terms, entropy is a measure of disorder, or more precisely, it is a measure of how many different microscopic arrangements of a system would look the same from the outside. A neatly organized deck of cards has low entropy. Shuffle it, and entropy increases. There are vastly more ways for 52 cards to be randomly arranged than there are ways for them to be sorted by suit and number. The second law of thermodynamics, one of the most ironclad principles in all of physics, states that entropy in a closed system never decreases. It can stay the same, or it can go up, but it cannot go down. This is why your coffee cools, why ice melts, why things fall apart. The universe, left to itself, always moves toward greater disorder. But black holes presented a problem. Imagine you have a box full of hot gas. That gas has entropy, a lot of it. Now imagine you throw that box into a black hole. The box crosses the event horizon, that point of no return where not even light can escape, and vanishes forever from the observable universe. The gas is gone, and so, apparently, is all its entropy. The second law seems violated. Entropy has decreased. You have hidden disorder behind a cosmic curtain, and the universe's entropy ledger no longer balances. Most physicists at the time assumed that black holes simply destroyed information. What fell in was gone, truly and irreversibly gone. And we would just have to accept that the second law had a loophole. Stephen Hawking himself initially believed this. Jacob Bekenstein refused to accept it. working under the supervision of John Archibald Wheeler, one of the greatest physicists of the 20th century, and the man who coined the term black hole. Bekenstein proposed something radical. Wheeler was a remarkable figure in his own right. He had worked on the Manhattan Project, contributed fundamental insights to general relativity, and mentored a generation of brilliant physicists, including Richard Feynman and Kip Thorne. He had a talent for asking the right questions, for finding the conceptual puzzles that would drive research forward for decades, and he had a particular fascination with the foundations of physics, with questions about information, reality, and the nature of existence itself. Wheeler encouraged Bekenstein to pursue his unconventional ideas about black hole entropy, even when other physicists were skeptical. He created the intellectual environment in which such ideas could flourish, and his own thinking about information and physics would prove prophetic. Bekenstein suggested that black holes themselves have entropy, enormous amounts of it, and this entropy was not stored inside the black hole, in its mysterious interior. It was proportional to something much more surprising: the surface area of its event horizon. Not the volume, the surface. Think about how counterintuitive this is. When you have a box of gas, its entropy depends on how much gas there is, which is determined by the volume of the box. Double the volume, and you can fit twice as much gas and roughly double the entropy. This makes intuitive sense. More space means more room for particles to arrange themselves in different ways. But Bekenstein was saying that for a black hole, the amount of information it could contain, the amount of entropy it could have, depended only on the area of its boundary. Like a hard drive where storage capacity depends on the size of its casing, not its thickness. A two-dimensional limit on three-dimensional content. This was a strange claim, and Bekenstein knew it. He was a graduate student proposing something that contradicted the intuitions of far more experienced physicists. But the logic was compelling. He proposed a formula. The entropy of a black hole, he said, was proportional to its horizon area divided by the Planck area, the tiniest meaningful unit of area in physics, roughly 10 to the minus 70 square meters. Each Planck-sized patch of the horizon contributed, in essence, one bit of information. Hawking was skeptical. In 1973, he published a paper acknowledging the formal similarity between black hole mechanics and thermodynamics. But he argued that black holes could not truly be thermodynamic objects. They had no temperature, they emitted nothing, and the analogy was merely mathematical, elegant, but not physical. And then, in 1974, Hawking performed the calculation that changed everything and proved himself wrong. Using the tools of quantum field theory applied to the curved spacetime around a black hole, Hawking discovered something astonishing. Black holes do emit radiation. They are not perfectly black. They glow faintly with a thermal spectrum that corresponds to a specific temperature, a temperature that depends on the black hole's mass. This radiation, now called Hawking radiation, arises from quantum effects at the event horizon. Virtual particle pairs, constantly flickering in and out of existence throughout space, can be torn apart by the immense gravitational gradient at the horizon's edge. One particle falls in, the other escapes as real radiation. The black hole loses mass in the process. It evaporates slowly over incomprehensible timescales. But here was the crucial point. If black holes have temperature, And if they radiate, then they must have entropy. This is not optional. Temperature and entropy are two sides of the same thermodynamic coin. If one exists, so must the other. Hawking's calculation not only confirmed Bekenstein's conjecture, it fixed the precise numerical coefficient that Bekenstein had been unable to determine. The entropy of a black hole, it turned out, equals exactly 1/4 of its horizon area, measured in Planck units. This is now called the Bekenstein-Hawking entropy formula. It is carved into Hawking's gravestone in Westminster Abbey, and it is one of the strangest equations in all of physics. Because here is what it means. A black hole the size of a small asteroid would have more entropy than all the matter in the observable universe. Not because black holes are complicated. They are famously simple, describable entirely by just 3 numbers: mass, charge, and spin. This is the no-hair theorem that Wheeler helped develop. Black holes have no distinguishing features beyond these 3 properties. Drop a library into a black hole, and from outside, it looks the same as if you dropped a random pile of rocks with equal mass. Yet black holes have enormous entropy because of what entropy actually measures at the deepest level. It measures information. It measures the number of distinct quantum states that could give rise to the same macroscopic appearance. To understand this, consider a cup of coffee. At the macroscopic level, you can describe it with a few numbers: temperature, volume, color. But at the microscopic level, the coffee is made of approximately 10 to the 25th molecules, each with its own position and velocity. There are an incomprehensibly vast number of different microscopic arrangements that would all look like the same cup of coffee. The entropy measures this number, or rather, the logarithm of this number, which keeps the values manageable. For ordinary objects, entropy scales with the number of particles, which scales with volume. More particles, more possible arrangements, more entropy. But for a black hole, the entropy scales with area, and it is enormous, far larger than the entropy of ordinary matter with the same mass. This means there must be an enormous number of quantum states hidden behind the event horizon, far more than we would naively expect from the simple macroscopic description. And all that information, all those quantum states, all the entropy that has ever fallen past the horizon of a black hole is encoded on a 2-dimensional surface. The boundary holds everything. In 1993, a Dutch theoretical physicist named Gerard Hooft was thinking about black holes at the Planck scale. He had won the Nobel Prize for his work on the strong nuclear force, and now he was grappling with the deepest questions in physics: how quantum mechanics and gravity fit together in extreme conditions. What Hooft realized was that the Bekenstein-Hawking formula was not just a peculiarity of black holes. It was a hint about the fundamental nature of reality. Consider what the formula says. The maximum amount of information that can fit inside any region of space is proportional to the area of the boundaries surrounding that region, not the volume, the area. This is true for black holes, because if you tried to cram more information into a given region than the formula allows, you would inevitably create a black hole, and the information would be bounded by the horizon area anyway. But if this is true for black holes, Hooft argued, it should be true for everything. It should be a universal principle. He called it dimensional reduction in quantum gravity. The idea was that physics at the Planck scale, where gravity becomes as strong as the other forces, is fundamentally two-dimensional. The three-dimensional world we experience is secondary, emergent, projected somehow from information stored on a lower dimensional surface, like a hologram. Leonard Susskind, a theoretical physicist at Stanford, saw Hooft's paper and immediately understood its implications. Susskind had been thinking along similar lines, wrestling with the black hole information paradox. The question of whether information that falls into a black hole is truly lost or somehow preserved. Susskind's path to this moment was unconventional. He had grown up in the Bronx, the son of a plumber, and had initially trained as an engineer before switching to physics. He worked as a plumber himself to pay for graduate school. This working-class background gave him a practical, no-nonsense approach to even the most abstract theoretical questions. If something did not make physical sense, he did not accept it, no matter how elegant the mathematics. And black holes destroying information did not make sense to him. Quantum mechanics, at its core, is deterministic. Given the complete quantum state of a system at one time, you can calculate its state at any other time, past or future. The equations are reversible. Information is conserved. This is not an optional feature of quantum mechanics. It is built into the mathematical structure of the theory. But Hawking's calculations seem to say that black holes violate this. They take detailed information, the quantum state of everything that falls in, and convert it into thermal radiation with no structure, no correlations, no memory of what it came from. When the black hole evaporates completely, the information is gone. Quantum mechanics is violated. Susskind refused to accept this conclusion. He believed that quantum mechanics was inviolable, that information could never be destroyed, that Hawking must be wrong somewhere, even if he could not immediately say where. The holographic principle gave him a framework for understanding how. In 1995, Susskind published a paper titled "The World as a Hologram." The title was not metaphorical. In this paper, Susskind laid out what he and T. Hooft were proposing in stark terms: the three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant two-dimensional surface. This became known as the holographic principle. To understand what the holographic principle claims, it helps to understand how actual holograms work. When you look at a holographic sticker, you are not seeing a flat image. You are seeing a three-dimensional scene reconstructed by light. The sticker itself is just a thin layer of material with an interference pattern etched into it, a pattern of microscopic grooves created when two laser beams interacted. One beam bounced off a real three-dimensional object. The other served as a reference. Where the beams met, they created a complex pattern of light and dark bands that encoded all the information about the object's shape, depth, and position. When light shines on that interference pattern later, it reconstructs the original wavefront. Your eyes receive light that looks exactly as if it came from a three-dimensional object. You can move your head and see the object from different angles. The depth is real, in some sense. Your brain interprets the light correctly, even though there is nothing behind the holographic surface but empty space. The key insight is this: a two-dimensional surface can encode complete three-dimensional information if the encoding is sophisticated enough. Every property of the original three-dimensional scene. Every angle, every shadow, every spatial relationship is faithfully recorded in the two-dimensional pattern. Nothing is lost. The holographic principle proposes that the universe works the same way. Everything happening inside a volume of space corresponds to something happening on the boundary of that space. And in principle, if you knew the complete state of the boundary, every quantum fluctuation, every bit of information, you could reconstruct everything inside. This sounds like philosophy. It sounds like a metaphor. But it turns out to have profound mathematical content. In 1997, a young Argentinian physicist named Juan Maldacena published a paper that would become the most cited article in the history of high-energy physics. His paper demonstrated something remarkable. In a specific mathematical setup, the holographic principle was not just an idea, it was an exact equivalence. Maldacena was working with a special kind of spacetime called anti-de Sitter space. This is not our universe. Our universe appears to have a small positive cosmological constant, making it more like de Sitter space. But anti-de Sitter space has properties that make it mathematically tractable. It has a boundary. And Maldacena showed that string theory in this five-dimensional anti-de Sitter space is exactly equivalent to a specific quantum field theory, a conformal field theory, living on its four-dimensional boundary. This is called the AD-CFT correspondence, and it is astonishing. On one side of the duality, you have a theory of quantum gravity, strings vibrating in 5 dimensions, space-time curving and warping, black holes forming and evaporating, all the weirdness of gravity at the quantum level. On the other side, you have an ordinary quantum field theory, no gravity at all, living on a flat boundary, particles and fields interacting according to familiar rules, no curved spacetime, no black holes, no apparent depth. And yet these two theories describe the same physics. They make identical predictions for every experiment. Anything you can compute in one theory has a precise translation in the other. A black hole in the interior corresponds to a thermal state on the boundary. Strings stretching across the bulk correspond to particles interacting on the surface. The mathematics fits perfectly. To grasp what this means, imagine discovering that a novel about a submarine exploring the ocean depths was, word for word, identical to a completely different novel about people living on a two-dimensional island, and that every event in one story perfectly corresponded to an event in the other, even though submarines and oceans never appear in the second book. The correspondence would seem miraculous. And yet, Maldacena showed that nature works this way. The AD-CFT correspondence is the most concrete realization of the holographic principle we have. It proves that the principle can work, that a full theory of quantum gravity can be entirely encoded on a lower dimensional surface without gravity. The boundary does contain everything about the bulk, and it changes how we think about reality. Here is the question that haunted physicists for decades. When something falls into a black hole, is the information about it lost forever? This is not an abstract worry. Quantum mechanics has a core principle called unitarity, which states that information is never destroyed. The laws of quantum mechanics are reversible. In principle, if you knew the complete quantum state of the universe at any moment, you could calculate both its entire past and its entire future. Nothing is truly lost, But Hawking's calculations seem to show that black holes violate this. The radiation they emit is thermal, random, featureless. It carries no information about what fell in. When the black hole evaporates completely, after trillions upon trillions of years, the information seems to be gone. A library fell into the hole, but only static came out. This is the black hole information paradox, and it plagued theoretical physics for decades. Some physicists sided with Hawking and accepted that information is lost. Others, like Susskind, insisted that unitarity must hold and the information must escape somehow. The debate was fierce, personal, and unresolved. The holographic principle offered a potential resolution. If all the information inside a black hole is encoded on its event horizon, then the information never truly falls inside. From the perspective of someone outside, the infalling matter spreads across the horizon like honey spreading on a spherical surface, getting stretched and smeared until it is distributed across the entire boundary. The information is never lost because it never left the boundary in the first place. This is called black hole complementarity, and it is deeply strange. It suggests that there are two valid but seemingly contradictory descriptions of what happens when something falls into a black hole. From the outside, everything stays on the surface. From the inside, for the infalling observer, you pass right through the horizon and plunge into the interior. Both descriptions are correct, but no single observer can access both. For years, this was somewhat philosophical. But then, in 2019, a breakthrough occurred. A team of physicists, including Ahmed Almheri, Netta Engelhardt, Donald Marolf, and Henry Maxfield, showed that Hawking's original calculation was incomplete. There were additional contributions, what they called islands in the radiation, that Hawking had not accounted for. When these were included, the calculation changed dramatically. The entropy of the radiation no longer increased forever. It followed the Page curve, exactly what quantum mechanics predicts if information is preserved. To understand why this mattered so much, you need to understand what the Page curve is. In the 1980s, Don Page, a student of Hawking's who had always disagreed with his mentor about information loss, made a simple but profound observation. If black holes obey quantum mechanics, their evaporation must follow a specific pattern. Consider a black hole that forms and then evaporates completely through Hawking radiation. At first, the radiation is maximally entangled with the black hole. This means the radiation, considered by itself, looks thermal and random, even though the total system, black hole plus radiation, is in a pure quantum state. As more radiation is emitted, the entropy of the radiation increases. The radiation gets more complicated, more entangled with the remaining black hole. This continues until the black hole is about half evaporated. At that point, called the Page time, something must change. After the Page time, if information is preserved, the entropy of the radiation must start to decrease. The radiation must start becoming correlated with itself, developing patterns and structures that encode the information about what fell into the black hole originally. By the time the black hole has completely evaporated, the radiation must be in a pure quantum state, complex and scrambled, but containing all the original information. When you plot the entropy of the radiation against time, this gives a curve that rises to a peak at the Page time and then falls back to zero. This is the Page curve. Hawking's calculation predicted something different. The entropy rising monotonically, never decreasing, approaching a maximum and staying there. This was the signature of information loss. For nearly 40 years, no one could reproduce the page curve from a gravitational calculation. The mathematics seemed intractable. Many physicists believed that some new physics beyond semi-classical gravity was needed, perhaps the full machinery of string theory or loop quantum gravity. Then came the 2019 breakthrough. Almheri and his collaborators showed that there is a way to reproduce the page curve using only semi-classical gravity, but you have to include a contribution that Hawking missed. The key insight involves something called the quantum extremal surface. This is a generalization of the minimal surfaces in the Ryu-Takayanagi formula. To calculate the entropy of the radiation properly, you have to find the right surface. And sometimes, surprisingly, that surface extends into the black hole interior. These interior contributions are the islands. They represent regions of the black hole interior that are, in a precise technical sense, encoded in the external radiation rather than in the black hole itself. As the black hole evaporates, these islands grow, capturing more and more of the interior. Eventually, they dominate the entropy calculation, causing the page curve to turn over. The result was stunning. The page curve emerged from pure gravity without invoking any exotic new physics. Information is preserved because it was never truly inside the black hole to begin with. Or rather, inside and outside are complementary descriptions, and the holographic encoding on the exterior captures everything. The black hole information paradox, which had resisted resolution for nearly 50 years, was finally yielding to the holographic principle. Let us pause and ask, what does all this mean for us? For the universe we live in? For reality as we experience it? The AD-CFT correspondence is mathematically precise, but it describes a universe that is not quite ours. Anti-de Sitter space has negative cosmological constant. Our universe has positive. Anti-de Sitter space has a clear boundary at infinity. Our universe has cosmological horizons that depend on where you stand. The correspondence is a proof of concept, not a direct description of our cosmos. But physicists believe the principle is more general, and when you start thinking through its implications, they become vertiginous. Consider the observable universe. Right now, from your position in space, light has had 13.8 billion years to travel since the Big Bang. But because space itself is expanding, the boundary of what you can see, the cosmological horizon, is not 13.8 billion light years away. It is about 46.5 billion light years away, a sphere of immense size surrounding you. And that sphere has an area. The holographic principle suggests that the maximum information content of the observable universe is proportional to this area. Not the volume enclosed, which is staggeringly large, but the surface area of the horizon. In Planck units, this works out to roughly 10 to the 122nd bits of information. The entire cosmos, everything you see when you look through a telescope, everything detected by every instrument ever built, could in principle be encoded on a two-dimensional surface at the boundary of the observable universe. In 2021, physicist Melvin Vopson calculated the amount of information stored in all the baryonic matter in the observable universe. all the protons, neutrons, and electrons that make up stars, planets, and people. His estimate, approximately 6 times 10 to the 80th bits, a number so large it is almost meaningless to human intuition, yet still vastly smaller than the holographic limit. The universe is nowhere near using its maximum storage capacity. The boundary can hold far more than what is currently written on it. But here is the strange part. Vobson noted that information could also be stored on the surface of space-time fabric itself, according to the holographic principle. The bits we can count in matter may be just a fraction of what is actually there. If reality is truly holographic, what does that mean? First, and most importantly, it does not mean the universe is an illusion, does not mean nothing is real. Holographic physicists are very clear about this. The three-dimensional world you experience is as real as anything can be. You can touch it, measure it, live in it. Gravity pulls you down. Light enters your eyes. Your neurons fire in complex patterns that constitute your thoughts. All of this is happening. The confusion arises because the word hologram has been so thoroughly co-opted by science fiction. In movies and television, holograms are projections, ghost images that you can walk through, visual tricks with no substance. This is emphatically not what physicists mean. When physicists say the universe might be holographic, they mean something precise and technical, that there exists a complete, mathematically equivalent description of all physics in fewer dimensions than we naively perceive. Not that our universe is fake, but that reality has multiple valid descriptions at different dimensional levels. Consider an analogy. The number 17 can be written as 17 in decimal notation, 10,001 in binary, or 17 in Roman numerals. These are different representations of the same underlying quantity. None is more real than the others. The number itself is independent of how we choose to write it. Similarly, the physics of our universe, the actual events that happen, the actual matter that exists, the actual forces that act, might be describable in 3 spatial dimensions with gravity, or equivalently describable in 2 spatial dimensions without gravity. The descriptions are different, but the physics is the same. Neither description is more real than the other. What the holographic principle says is that there is a mathematically equivalent description of all this physics that uses fewer dimensions. It says that depth, in some fundamental sense, is emergent rather than fundamental. The information encoded on a lower dimensional surface is sufficient to generate everything you experience in higher dimensions. Think of it this way. When you watch a movie, you see characters and landscapes and motion and depth. The movie seems to contain a world, but all of that comes from a sequence of flat images projected very quickly. The flatness of the frames does not make the story unreal. It just means the story has a particular kind of structure, a particular relationship between what is fundamental, the frames, and what emerges, the experience. The holographic principle suggests that the universe has this structure at the deepest level. Space-time itself, the fabric in which all events occur, may emerge from something more fundamental, something that lives on a boundary, and there is growing evidence that this something is information. John Archibald Wheeler, Bekenstein's doctoral supervisor, the man who named black holes, spent the last decades of his career developing a radical idea. He called it from bit. The idea was that physics, at its most fundamental level, is not made of particles or fields or even space-time. It is made of information. Every physical quantity, every interaction, every piece of matter derives its existence from answers to yes or no questions, from bits of information. Wheeler wrote in 2003, "Every ite, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely from the apparatus elicited answers to yes or no questions, binary choices, bits." This sounds mystical, but it has mathematical substance. In 2011, Eric Verlinde proposed that gravity itself might be an entropic force, not a fundamental interaction, but an emergent phenomenon arising from changes in information on a holographic screen. When you move a mass closer to another mass, you change the information on the screen between them, and this change manifests as gravitational attraction. The idea is controversial and not yet proven, but it points to a deep connection. The laws of physics we discover may be thermodynamic equations of state, describing how information flows and organizes at a boundary. Gravity, space-time, perhaps even the quantum fields of the Standard Model. All of it might be shadows on a cosmic cave wall, projected from a two-dimensional reality of pure information. Plato imagined prisoners chained in a cave, watching shadows on a wall and mistaking them for reality. The holographic principle suggests that in some sense, we are all in the cave. But the cave is the universe itself, and the shadows are space-time. Can we test this? In 2008, a physicist named Craig Hogan at Fermilab proposed that if space-time is fundamentally grainy at the Planck scale, if it is built from discrete bits of information on a holographic surface, then there should be a specific kind of noise in our measurements of space. This holographic noise would manifest as tiny random fluctuations in the positions of objects, undetectable in ordinary circumstances, but potentially visible in extremely precise instruments. At the time, Hogan noticed that the GEO 600 gravitational wave detector in Germany was picking up unexplained noise at high frequencies. He wondered if this might be holographic noise, the static of reality's fundamental pixelation bleeding through into our measurements. It was a tantalizing possibility, but to test it properly, Fermilab built a dedicated instrument, the holometer. This device consisted of two interferometers capable of detecting fluctuations as small as an atometer, 1/1000th of a meter. If space was jittering at the Planck scale, the holometer might see it. In 2015, after a year of data collection, the results came in. The holometer found nothing. More precisely, it found no holographic noise of the type Hogan had predicted. The specific model of pixelated space-time he had proposed was ruled out with high statistical confidence. Space, at the scale the holometer could probe, appeared smooth. This was disappointing in one sense, but Hogan and his collaborators were quick to point out that this was just one model. The holographic principle itself is far more general, and there are many ways the fundamental graininess of space-time might manifest. The holometer proved that space could be probed at unprecedented scales. It opened a new experimental window. The search continues. In 2020, a paper by Egan and Lineweaver estimated the entropy of the observable universe at roughly 10 to the 104th bits, dominated by supermassive black holes at the centers of galaxies. They also estimated the entropy of the cosmological horizon itself at around 4 × 10 to the 122nd bits. The numbers match. The universe seems to be obeying its holographic bounds. There is another implication of the holographic principle that deserves mention, because it touches on the question of what we are. If information is fundamental, if the physical world emerges from bits encoded on a cosmic surface, then you, too, are made of information. Your memories, your personality, your sense of self, the specific arrangement of atoms that constitutes your body. All of it is data, patterns written on reality's boundary. This does not diminish you. Information is not ephemeral or ghostly. In the holographic view, information is the most real thing there is. It is the substance from which physics itself is made. You are not a ghost in a machine. You are a pattern in the universe's code, a standing wave of information that has persisted and grown and become conscious of itself. And if information is conserved, if unitarity holds, if the holographic principle is true, then in some deep sense, you are never lost. The information that makes you who you are cannot be destroyed. It might be scrambled, dispersed, encoded in forms too complex to recover, but it is never gone. The universe keeps its records. Whether this is comforting or terrifying depends on your philosophy. But it is what the physics seems to say. Let me tell you about a peculiar experiment that was never performed, but that illuminates what holography really means. Imagine you could build a perfectly spherical mirror, polished to atomic smoothness, and make it large enough to enclose a significant region of space. Inside this mirror sphere, you place various objects: a chair, a lamp, perhaps a small aquarium. Then you seal the sphere and observe only its surface. An observer on the surface would see reflections, complex patterns of light encoding everything inside the sphere. With sufficiently detailed observations of the surface alone, they could, in principle, reconstruct the complete three-dimensional arrangement of objects within. The surface contains all the information about the interior. This is a crude analogy, but it captures something essential about the holographic principle. The boundary of a region, whether a mirror's surface, a black hole's event horizon, or the cosmological horizon of the observable universe, contains all the information needed to describe what is inside. The encoding may be complex, scrambled beyond immediate recognition, but it is complete. Now push this further. In the mirror example, we think of the objects as primary and the reflections as derived. The chair exists first, its reflection is secondary, but the holographic principle suggests that this priority might be backwards, or at least that the distinction might be meaningless. If the boundary description is complete, if it contains all the information, then it is not clear in what sense the interior is more real than the surface. Both descriptions are valid. Both make the same predictions. Both are physics. The question of which is really real may not have an answer. This is what makes holography so philosophically disorienting. We are used to thinking of surfaces as wrappings, as exteriors to interiors, as secondary to the bulks they enclose. The holographic principle inverts this, or rather, makes the distinction irrelevant. The universe may not have an inside and an outside in the way we imagine. It may just have descriptions at different levels, equivalent and complementary. There is a deeper puzzle that holography raises, one that touches on the nature of emergence itself. When we say that space-time emerges from information on a boundary, what do we mean by emergence? In everyday science, emergence refers to properties that arise from collective behavior but are not present in individual components. Wetness emerges from collections of water molecules. No single molecule is wet. Temperature emerges from the average motion of particles. No single particle has a temperature. These emergent properties are real and important, but they are also, in some sense, reducible. If you knew everything about the molecules, you could derive the wetness and temperature. Holographic emergence is more radical. It is not just that certain properties emerge from boundary data. It is that space itself emerges. The extra dimension in the bulk is not present in the boundary theory at all, not even implicitly. It is genuinely new, constructed from the patterns of information on the surface. How can something come from nothing? How can 3 dimensions arise from 2? The answer involves the concept of entanglement once again. The extra dimension corresponds, in a precise mathematical sense, to the structure of entanglement on the boundary. Different patterns of entanglement give rise to different geometries in the bulk. Strong entanglement between nearby boundary regions produces connected, smooth spacetime. Weak or no entanglement produces fragmented, disconnected geometry. The bulk is not hiding somewhere behind the boundary. It is constructed from the boundary's quantum correlations. Space is made of entanglement. This is profoundly strange, and not everyone is comfortable with it. Some physicists argue that we should not say space-time emerges, but rather that it is dual to, or equivalent to, the boundary description. The language of emergence suggests a priority, the boundary as fundamental, the bulk as derivative, that may not be justified. Others embrace emergence fully. They argue that the holographic principle is telling us something deep about the nature of reality, that space and time are not fundamental features of the universe, but are constructed, emergent, derived from something more basic. The search for quantum gravity, in this view, is really a search for the principles by which space-time is constructed. Either way, the implications are profound. The arena in which physics takes place, the space-time in which events occur, is itself a physical phenomenon, requiring explanation and subject to laws. The question, what is space, would have an answer beyond mere geometry. Space is the projection of quantum correlations from a holographic surface. Let us address the simulation hypothesis, because it inevitably arises when holography is discussed, and it is important to distinguish physics from speculation. The simulation hypothesis, popularized by philosopher Nick Bostrom and countless science fiction stories, suggests that our universe might be a computer simulation running on hardware in some higher reality. If this were true, we would be like characters in a video game, living in a constructed reality without knowing it. The holographic principle is sometimes confused with this idea, but they are fundamentally different. The simulation hypothesis is about what exists outside our universe, about some hypothetical substrate on which our reality is computed. It is not a scientific theory, because it makes no testable predictions. If we are in a simulation, the simulators could make anything happen, so nothing could ever falsify the hypothesis. It is metaphysics, not physics. The holographic principle is about the structure of our universe itself, about equivalent descriptions at different dimensional levels, all of which are equally real. It makes specific, testable predictions about black hole entropy, about quantum gravity, about the behavior of entanglement in certain systems. It is science. More importantly, the holographic principle does not imply that we are characters in a program or that some external agent is running our reality. The holographic encoding is not a computer file. It is the universe itself, described in a different mathematical language. There is no screen, no projector, no observer outside watching. The boundary is part of the universe, not something separate from it. When physicists say the universe might be a hologram, they do not mean anything like the simulation hypothesis. They mean that reality has a mathematical structure in which lower dimensional descriptions are equivalent to higher dimensional ones. They mean that information, not matter, may be fundamental. They mean that space and time may emerge from something deeper. These are radical claims, but they are claims about the actual structure of our universe, testable in principle and constrained by evidence. They are not claims about external simulators or arbitrary computer programs. The holographic principle also raises questions about consciousness that, while speculative, are worth considering. If we are patterns of information encoded on a cosmic boundary, what does that mean for subjective experience? What does it mean to be conscious if you are data? This is not a scientific question. Consciousness is not well enough understood to say anything definitive, but it is a natural one to ask. One perspective is that nothing changes. Whatever consciousness is, it is a property of certain patterns of information processing. If those patterns exist, whether in a three-dimensional brain or equivalently encoded on a two-dimensional surface, the consciousness exists too. The holographic encoding does not diminish or alter the experience. It just describes it differently. Another perspective is that holography deepens the mystery. If space itself is emergent, if the distance between neurons in your brain is constructed from quantum entanglement on a boundary, then the binding problem of consciousness, how do separate neural processes combine into unified experience, might have a different character. Perhaps the non-local correlations that build spacetime also contribute to the unity of consciousness. This is speculation, not physics. We do not understand consciousness well enough to know how it relates to the fundamental structure of reality. But the holographic principle provides a new framework for thinking about these questions, one in which information is primary and space is secondary. At minimum, holography suggests that minds, like everything else, are patterns of information. Whatever makes you who you are is encoded in the state of the universe, distributed across the holographic boundary, preserved as long as information is conserved. You are not a ghost in a machine. You are a wave in the cosmic data, a pattern that persists and evolves according to physical law. Where does all this leave us? The holographic principle remains a conjecture, not a proven theorem. The ADS-CFT correspondence is mathematically rigorous, but it describes a universe different from ours. Extending holography to de Sitter space, to a universe with positive cosmological constant like the one we inhabit, is one of the great open problems in theoretical physics. Researchers at institutions around the world are working on it. Progress is steady, but slow. What we can say is this: some of the deepest problems in physics have yielded to holographic thinking. The black hole information paradox, which seemed to threaten the foundations of quantum mechanics, is being resolved through holographic methods. The nature of quantum gravity, that elusive theory uniting Einstein's spacetime with quantum uncertainty, seems to be holographic at its core. The most successful approaches, string theory, M theory, the web of dualities connecting them, all point toward boundaries that contain bulks, surfaces that encode volumes. Leonard Susskind, reflecting on the journey from black hole entropy to the AD-S-CFT correspondence, said that Maldacena's result brought the holographic principle to center stage by providing an actual working example. It transformed holography from a speculative idea into a research program, from philosophy into physics. And the implications, if we follow them to their logical conclusion, are profound. If the holographic principle is true, then the distinction between inside and outside, between volume and surface, between 3 dimensions and 2, is not as fundamental as we thought. It is a matter of description, not substance. The universe has layers of reality, dual descriptions, equivalent theories that look completely different but say the same thing. What we call space might emerge from something deeper, something we are only beginning to understand. Let us pause and appreciate the human story behind these discoveries, because physics is not just equations and abstractions. It is the work of individuals wrestling with the deepest questions. Jacob Bekenstein died in 2015, just months after receiving the American Physical Society's Einstein Prize for his groundbreaking work on black hole entropy. He was 68 years old. The prize citation honored him for his groundbreaking work on black hole entropy, which launched the field of black hole thermodynamics and transformed the long effort to unify quantum mechanics and gravitation. Bekenstein never saw the 2019 breakthrough that finally derived the page curve from semi-classical gravity. He never saw the full vindication of his intuition that information is conserved, that entropy scales with area, that black holes are not cosmic trash cans, but cosmic hard drives. But the framework he created in 1972 made all of it possible. Stephen Hawking died in 2018, having lived for 55 years after being diagnosed with motor neuron disease at age 21. He had initially opposed Bekenstein's ideas, then provided the crucial calculation of black hole radiation that confirmed them. He had argued for decades that information is lost in black holes, then gradually came to accept that it is preserved. In 2004, he famously conceded a bet with John Preskill about the information paradox, giving Preskill a baseball encyclopedia to symbolize the information that escapes from black holes. Leonard Susskind, now in his 80s, continues to work on quantum gravity, black holes, and the foundations of physics. His early work with Hooft on holography, his development of black hole complementarity, and his contributions to string theory have shaped the field for decades. Juan Maldacena, whose 1997 paper remains the most cited in high-energy physics history, works at the Institute for Advanced Study in Princeton, the same institution where Einstein spent his final years. He continues to explore the implications of the AD-S-CFT correspondence. Maldacena was just 29 years old when he published the paper that would change theoretical physics. He had been a graduate student at Princeton just a year earlier, working under Curtis Callan on problems in string theory. The ADS CFT correspondence emerged from his efforts to understand a specific string theory setup involving brains, extended objects in string theory on which strings can end. The impact was immediate, within months of Maldacena's paper appearing on the R-CISF preprint server. Hundreds of physicists around the world had begun working on its implications. By 2015, the paper had accumulated over 10,000 citations, making it the most cited paper in the history of high-energy physics. Entire research programs, entire careers, entire subfields of physics emerged from those initial calculations. Gerard at Hooft, the Nobel laureate who first proposed dimensional reduction in quantum gravity, continues to work on foundational questions in physics at the University of Utrecht. His 1993 paper planted the seed that grew into the holographic principle. Hooft had won the Nobel Prize in 1999 for his work on the quantum structure of electroweak interactions, the theory that unifies the electromagnetic force with the weak nuclear force. But his interests ranged far beyond particle physics into quantum gravity, black holes, and the foundations of physics itself. His 1993 paper on dimensional reduction was not celebrated at the time. It appeared in conference proceedings rather than a major journal. But its ideas proved enormously influential. These are the human beings who gave us this understanding. Their names may be less famous than Einstein's or Newton's, but their work may ultimately prove just as revolutionary. They have shown us that the universe may have a structure we never suspected, that space and time may emerge from something deeper, that information may be the fundamental stuff of which reality is made. Let us address one more question that often arises. Does the holographic principle mean we should stop trusting our senses? No, your senses are accurate. When you see a tree, there really is a tree there. When you feel the ground beneath your feet, the ground is really there. The three-dimensional world you perceive is not an illusion or a mistake. It is one valid description of reality, the description that is most useful for organisms like us, evolved to navigate environments on human scales. What the holographic principle says is that there is another description, equally valid, that uses fewer dimensions. This does not make the three-dimensional description wrong. It makes it one of multiple correct ways to describe the same underlying physics. Consider a related situation from ordinary physics. When you look at a flowing river, you see water moving, eddies swirling, waves propagating. This is a perfectly accurate description. But there is another description. The positions and velocities of approximately 10 to the 26th water molecules, following the laws of classical mechanics. Both descriptions are correct. They are descriptions at different levels of detail. Similarly, the holographic description and the three-dimensional description are both correct. They capture the same physics in different mathematical languages. Neither is an illusion. Both are reality, described differently. The holographic principle does not undermine your experience. It enriches it. It reveals that the world you inhabit has a deeper structure than you knew, a hidden simplicity beneath apparent complexity, a unity connecting what seemed separate. Let me leave you with an image. The observable universe extends 46.5 billion light-years in every direction. It contains something like 2 trillion galaxies, each with hundreds of billions of stars orbited by countless planets suffused with dark matter and energy we cannot see but whose gravity shapes everything. It is vast beyond human comprehension, ancient beyond human timescales, complex beyond human calculation. And yet, all of it, every galaxy, every star, every planet, every person who has ever lived, every thought anyone has ever had, might be encoded on a two-dimensional surface at the edge of everything we can observe, a sphere of information written in bits so small they approach the limits of physical meaning, the cosmic horizon, that boundary between what light can reach and what lies forever beyond, holding within its area the complete description of everything inside. We are, perhaps, not beings swimming through a three-dimensional ocean. We are patterns written on a cosmic page, shapes in a higher dimensional shadow. Information become conscious of itself, looking up at the boundary of its own encoding and wondering what it means. The universe filled with galaxies, stars, planets, houses, boulders, and people is a hologram, an image of reality coded on a distant, two-dimensional surface. That is what Leonard Susskind wrote in 1995. And decade by decade, calculation by calculation, the evidence has mounted that he was right. You set down your phone. You look around the room. The walls are solid. The floor supports you. Light streams through the window, casting shadows that shift as you move. Everything seems so real, so three-dimensional, so obviously present. And it is. It is as real as anything can be. But reality, we are learning, is stranger than it appears. It has depths we did not expect and shallows that contain more than we imagined. The boundary holds the bulk. The surface encodes the volume. Information is fundamental, and everything else emerges. We might be living on the surface of a black hole in some generalized sense. We might be projections on a cosmic screen. We might be patterns in the universe's memory, written in Planck-sized bits on a boundary we cannot see. The physicists who developed these ideas, Bekenstein with his thought experiments about entropy, Hawking with his radiation that makes black holes shine, Hooft with his dimensional reduction, Susskind with his holographic vision, Maldacena with his mathematical proof of principle, were not trying to undermine our sense of reality. They were trying to understand it more deeply. They followed the equations where they led, even when the destination was strange. And the equations led here, to the possibility that the universe is holographic, that depth is emergent, that information is fundamental, that the boundary holds everything within it. This is not mysticism dressed up as science. It is science reaching into realms that once belonged to mystics and philosophers. What is reality? What is existence? What are we? These ancient questions now have physical content, mathematical structure, experimental implications. We live in an extraordinary time. The questions that humans have asked since they first looked at the stars are being answered, not with myths and stories, but with equations and evidence. The answers are strange, often stranger than the myths, but they have the advantage of being true, or at least of being our best current approximation to truth. The holographic principle is part of this unfolding understanding. It may not be the final word. Science never has a final word, but it is a word worth speaking. It tells us something profound about the cosmos and our place within it. And if it is true, if the three-dimensional world of ordinary experience really is a hologram, an image of reality coded on a distant two-dimensional surface, then the question is not whether the universe is real. It is what we mean by real in the first place. But let us go deeper, because to truly understand the holographic principle, we need to understand the units in which reality is written. We need to understand the Planck scale. Max Planck was a German physicist working at the turn of the 20th century. In 1899, he discovered something remarkable by combining just three fundamental constants of nature: the speed of light, Newton's gravitational constant, and what we now call Planck's constant. He could derive a natural system of units that belonged not to any human convention, but to the universe itself. The Planck length is roughly 1.6 times 10 to the minus 35 meters. To say this is small does not begin to capture it. If you took a single atom and magnified it to the size of the observable universe, the Planck length would still be smaller than a single atom in that magnified picture. It is approximately 10 to the 20th times smaller than a proton. It is so small that the very concept of distance may break down at this scale. The Planck time is similarly extreme, about 5.4 times 10 to the minus 44 seconds. This is the time it takes light to travel one Planck length. At intervals shorter than this, our understanding of time itself becomes uncertain, and the Planck area, the Planck length squared, is the fundamental unit of area in the holographic accounting. Each Planck area on a boundary represents roughly one bit of information, one yes or no answer, one fundamental quantum of reality's data. Think about what this means. The event horizon of a black hole, measured in Planck areas, tells you how many bits of information the black hole contains. The Bekenstein-Hawking formula says entropy equals 1/4 of the area in Planck units. So a black hole with a horizon area of 4 Planck areas has an entropy of 1. A black hole with 400 Planck areas has an entropy of 100, and so on. The numbers get big very quickly. A black hole with the mass of our Sun, a relatively small black hole by cosmic standards, would have an event horizon area of roughly 10 to the 77th Planck areas, corresponding to about 10 to the 77 bits of entropy. Of that is more information than in all the books ever written, all the data ever stored on all the computers ever built, all the memories ever held in all the brains that have ever existed, multiplied together many times over. And that is a small black hole. The supermassive black holes at the centers of galaxies are millions to billions of times more massive. Their entropy is correspondingly larger. Astronomers estimate that the total entropy of all the black holes in the observable universe is roughly 10 to the 104th bits, a number so large that writing it out in full would require more zeros than atoms in your body. This entropy dominates the universe's total. Stars, gas clouds, planets, people, all the ordinary matter we see contributes only a tiny fraction. The cosmos is, in entropic terms, a collection of black holes with some dust around the edges, and all that entropy, all that information, resides on two-dimensional surfaces. The question arises, why should nature work this way? Why should information be bounded by area rather than volume? There are several ways to approach this question. The simplest involves what physicists call the Bekenstein bound. Imagine you have a region of space with a given energy content and a given size. You might think you could pack as much information into that region as you like. Just use smaller and smaller components, denser and denser storage media. But there is a limit. If you try to concentrate too much energy into too small a space, you will form a black hole. And once you have a black hole, its entropy is determined by its horizon area. You cannot beat the black hole's information density. This means the black hole represents the maximum information storage for any region of a given size. And since a black hole entropy scales with area, maximum information scales with area. The Bekenstein bound follows. The entropy of any region cannot exceed 1/4 of its bounding area in Planck units. But this still seems strange. Why should gravity set a limit on information? What does the curvature of spacetime have to do with data storage? The answer may lie in the nature of quantum mechanics itself. In ordinary quantum mechanics, we describe systems using states in a Hilbert space, an abstract mathematical space whose dimension tells us how many distinct states the system can occupy. A system with more possible states has a larger Hilbert space. A coin has a two-dimensional Hilbert space, heads or tails. A pair of coins has a four-dimensional space, heads heads, heads tails, tails heads, tails tails. For ordinary quantum fields in flat spacetime, the dimension of the Hilbert space grows exponentially with the volume of the region you are describing. More space, exponentially more possible states. This is what we would naively expect. But gravity changes everything. When gravity is included, the Hilbert space cannot grow without bound. If you try to add more quantum states to a region, you add energy. Add enough energy and you form a black hole. The black hole's entropy then depends on area, not volume. The dimension of the Hilbert space is bounded by the exponential of the area. This is a dramatic reduction. In a world with gravity, there are far fewer fundamental degrees of freedom than we would otherwise expect. Reality is, in some sense, more economical than it appears. The vast three-dimensional world we inhabit can be fully described by a two-dimensional data structure. Some physicists find this disturbing. Others find it beautiful. But the mathematics is unambiguous. Gravity demands holography. Let us return to the ADS-CFT correspondence and examine it more closely, because it is the best window we have into how holography actually works. Anti-de Sitter space, ADS for short, is a solution to Einstein's equations of general relativity with a negative cosmological constant. Picture a universe that curves inward on itself, like the inside of a bowl, but in all spatial directions. It is not expanding or contracting uniformly, but instead has a peculiar geometric structure where the boundary is infinitely far away in some sense, yet still accessible mathematically. In the simplest version of the correspondence, we consider five-dimensional ADS space with a radius r. This space has a four-dimensional boundary, a surface at infinity with one time dimension and three space dimensions, much like our everyday world. Juan Maldacena showed that string theory on this five-dimensional space is exactly equivalent to a specific quantum field theory on the four-dimensional boundary. The boundary theory is a conformal field theory, a theory invariant under certain scaling transformations, with the special feature of being supersymmetric. It is called Sn equals 4 super Yang-Mills theory. And while it does not describe our actual world in detail, it shares many important properties with theories that might. What makes the correspondence useful is that it relates strong coupling on one side to weak coupling on the other. When the boundary theory is strongly interacting, when particles scatter and bind and do complicated things that are hard to calculate, the bulk theory is weakly curved. Classical gravity becomes a good approximation, and vice versa. When gravity in the bulk is strongly quantum, the boundary theory becomes weakly coupled and amenable to ordinary methods. This is called strong-weak duality, and it has revolutionized theoretical physics. Problems that seemed impossibly hard in one description become tractable in the other. Physicists have used ADS CFT to study everything from the quark-gluon plasma created in heavy ion collisions to the properties of superconductors to the thermodynamics of black holes. The holographic dictionary translates between languages, making the incomprehensible comprehensible. But perhaps the most important application has been to black holes. In ADS CFT, a black hole in the bulk corresponds to a thermal state on the boundary. The temperature of the black hole equals the temperature of the boundary system. The entropy of the black hole equals the entropy of the thermal bath. Everything matches. This means the information about what fell into the black hole is encoded in the boundary theory. It is not hidden behind the horizon in an inaccessible interior. It is spread across the boundary, scrambled into complex correlations, but present. The boundary theory is manifestly quantum mechanical, with unitary evolution and no information loss. Therefore, the bulk theory must preserve information too. The black hole information paradox, which seemed to threaten the foundations of physics, is resolved by construction in ADS CFT. Information is conserved because it was never inside the black hole to begin with, or rather, inside and outside are complementary descriptions of the same physics, and the outside description is holographic. One of the most striking consequences of AD CFT is the Ryu-Takayanagi formula, discovered by Shinsei Ryu and Tadashi Takayanagi in 2006. This formula relates entanglement entropy, a purely quantum mechanical concept measuring how correlated two regions of a system are, to geometry in the bulk. Specifically, it says that the entanglement entropy of a region on the boundary equals the area of a special surface in the bulk, the minimal surface that is anchored to the boundary of that region. This is extraordinary. Entanglement is one of the most mysterious features of quantum mechanics, the phenomenon that Einstein called spooky action at a distance. It describes correlations between particles that are stronger than any classical correlation, connections that persist even when the particles are separated by vast distances. And Ryu and Takayanagi showed that these quantum correlations translate directly into geometry. Entanglement becomes area. The implications are profound. If entanglement equals geometry, then geometry emerges from entanglement. The fabric of spacetime, the arena in which all physics takes place, is woven from quantum correlations on a boundary. Spacetime is not fundamental. It is emergent, stitched together from the entanglement structure of an underlying quantum system. This idea has been explored extensively by Mark van Ramsdonk, Brian Swingle, and many others. They have shown that regions of spacetime can be disconnected, literally torn apart, if the corresponding boundary regions become disentangled. Conversely, entangling previously uncorrelated regions creates geometric connections between them. Spacetime has the connectivity it has because of the pattern of quantum entanglement on the boundary. Van Ramsdonk described this memorably in a 2010 paper titled Building Up Spacetime with Quantum Entanglement. He argued that entanglement is the glue that holds spacetime together. Without it, space would fragment into disconnected pieces. The smooth, continuous fabric of reality that we take for granted is maintained by an intricate web of quantum correlations. This is not just a poetic metaphor. It has mathematical substance. Using the Ryu-Takayanagi formula and its generalizations, physicists can calculate exactly how changes in entanglement correspond to changes in geometry. They can show that adding or removing entanglement modifies the bulk spacetime in predictable ways. The correspondence is precise and testable, at least within the ADS-CFT framework. One of the most striking results comes from considering the thermofield double state, a particular quantum state that involves two copies of the same system maximally entangled with each other. In the ADS-CFT correspondence, this state corresponds to a wormhole, a tunnel through spacetime connecting two distant regions. The wormhole exists because the two boundary regions are entangled. Break the entanglement, and the wormhole pinches off. This led to a remarkable slogan: ER equals EPR. ER refers to Einstein-Rosen bridges, what we now call wormholes, which were first described by Einstein and Nathan Rosen in 1935. EPR refers to the Einstein-Podolsky-Rosen paradox, the famous thought experiment about quantum entanglement that Einstein also proposed in 1935. The slogan, advanced by Juan Maldacena and Leonard Susskind, suggests that these two phenomena, wormholes and entanglement, are the same thing described in different languages. Einstein spent years trying to understand the relationship between quantum mechanics and gravity. He sought a unified theory that would explain both. It is poetic and perhaps appropriate that the answer seems to involve entanglement, the very phenomenon he found most troubling about quantum mechanics. We have spoken about boundaries and surfaces, but we have not been precise about which surface the holographic information lives on. This matters because different boundaries give different physics. For a black hole, the relevant surface is the event horizon, the sphere of no return surrounding the singularity. Information about what fell in is encoded on this surface, spread across it in a pattern that looks random but contains the complete record. For anti-d Sitter space, the relevant surface is the boundary at infinity, the edge of the universe in that particular geometry. The boundary theory lives there, and all the physics in the bulk emerges from it. But what about our universe? Our universe is not anti-d Sitter. It appears to be flat or nearly flat, with a small positive cosmological constant that is causing space to expand at an accelerating rate. We do not have a boundary at infinity. We have cosmological horizons, surfaces beyond which we cannot see, not because of black hole gravity, but because space is expanding faster than light can cross it. The cosmological horizon is different for different observers. You have one. I have one. They are centered on each of us, spheres 46 billion light-years in radius, enclosing everything that light has had time to reach since the Big Bang. Beyond that sphere, from our perspective, nothing can affect us. Nothing can be observed. Nothing can send signals. Can holography work for cosmological horizons? This is one of the great open questions in theoretical physics. In 2001, Andrew Strominger proposed what he called the DS-CFT correspondence, a version of AD-S-CFT that would apply to de Sitter space, a universe with positive cosmological constant like ours. The boundary in this case would be in the future, the surface at future infinity toward which our universe is asymptotically expanding. A quantum field theory on that boundary would encode all the physics in the de Sitter bulk. But DS-CFT is much less well understood than AD-S-CFT. The mathematics is harder. The boundary is not accessible to observers in the bulk. We are all trapped inside, never reaching future infinity. The correspondence, if it exists, works in ways that are subtle and still being explored. Some physicists have proposed that each cosmological horizon might function as a holographic screen for the observer at its center. You are surrounded by a horizon, and the information about everything inside your observable universe is encoded on that horizon. The degrees of freedom are bounded by its area, approximately 10 to the 122nd bits, and all of physics unfolds as a projection from that cosmic boundary. This is speculative. It is philosophy as much as physics at this stage, but it points to something profound. The very concept of inside may be illusory. We think we are in a three-dimensional universe, moving through space, extending in depth. But depth might be constructed, emergent, derived from information on a surface we cannot see. There is a thought experiment that helps clarify what holography means and does not mean. It is sometimes called the holographic paradox, though it is not really a paradox, just a puzzle that tests intuition. Imagine you're about to fall into a black hole. You cross the event horizon. From your perspective, nothing special happens. The horizon is just a mathematical surface in space, not a physical barrier. You continue inward, toward the singularity. You have perhaps a few seconds of proper time before tidal forces tear you apart. But for those seconds, you are inside the black hole. Now consider an observer watching you from outside. According to them, you never cross the horizon at all. Instead, due to time dilation, your image slows down and fades, asymptotically approaching, but never reaching the horizon. Your information in their description remains spread across the horizon surface forever. Both descriptions are correct. Both are valid. But they cannot both be simultaneously accessed by any single observer. You cannot be inside the black hole looking out and outside the black hole looking in at the same time. The holographic principle holds because complementary descriptions never contradict within any single observer's experience. This is called black hole complementarity, and it resolves an apparent paradox. The information is both inside and on the surface, depending on who is asking and what they can measure. Reality has multiple valid descriptions that would seem contradictory if you tried to hold them simultaneously, but you cannot hold them simultaneously. Physics remains consistent. The broader lesson: holography does not say that three-dimensional space is an illusion. It says that three-dimensional space has an equivalent two-dimensional description. These are not competing claims about what is real. They are complementary perspectives on the same reality. The interior of a black hole is real to someone falling in. The holographic encoding on the horizon is real to someone watching from outside. Both are physics. We have focused on theoretical developments, but what about experiments? Can holography be tested? The answer is partially, with great difficulty, and we are trying. As mentioned, the Fermilab holometer searched for holographic noise, random jitter in spacetime that would indicate discrete Planck scale structure. It found none at the level predicted by one particular model, but that model was specific and somewhat speculative. The holographic principle itself is more general and makes fewer precise predictions about what experiments should see. Other tests are more indirect. The existence of black hole entropy, confirmed through multiple theoretical approaches and consistent with observations of black hole mergers via gravitational waves, supports the Bekenstein-Hawking formula that underlies holographic thinking. The thermodynamic behavior of black holes, now understood in exquisite detail, matches holographic predictions. In 2016 and 2017, physicists detected gravitational waves from merging black holes using the LIGO and Virgo detectors. These observations confirmed Einstein's general relativity to extraordinary precision and provided new data about black hole properties. The ring-down phase of black hole mergers, when the newly formed black hole settles into equilibrium, carries information about the black hole's entropy and temperature. So far, everything matches the Bekenstein-Hawking predictions. Future experiments may probe deeper. The Laser Interferometer Space Antenna, LISA, planned for the 2030s, will detect gravitational waves from supermassive black hole mergers and could test predictions about black hole entropy at much larger scales. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, might reveal subtle imprints of holographic physics on primordial fluctuations. Some physicists have even proposed that quantum properties of spacetime might be detectable through carefully designed laboratory experiments with entangled particles. We are not yet at the point of definitive tests. The holographic principle makes predictions at the Planck scale, and the Planck scale is almost unimaginably far from our experimental reach. It is as if we are trying to read a book by examining the shadows it casts from a great distance, but shadows contain information, and we are learning to read them. There is one more aspect of the holographic principle that deserves exploration: its connection to quantum computation. In recent years, physicists have realized that black holes are not just thermal systems. They are computational systems. They process information in specific ways, scrambling inputs into outputs with extraordinary efficiency. A black hole takes whatever falls in, however complex, however structured, and randomizes it across its horizon in a time proportional to the logarithm of its entropy. This is called scrambling, and black holes are the fastest scramblers in nature. John Preskill and his collaborators at Caltech have studied the relationship between black holes, quantum error correction, and the structure of spacetime. They found that the way information is encoded on a holographic boundary resembles the way quantum computers encode information in error-correcting codes. The bulk spacetime can be thought of as the logical information. The boundary data is the physical encoding. Redundancy in the boundary allows the bulk to be reconstructed even if parts of the boundary are lost. This is deeply suggestive. It hints that the machinery of quantum computation is not just a technological tool, but a window into the nature of reality. The universe itself may operate according to principles of quantum information processing. Spacetime may be built from qubits, quantum bits of information, entangled and correlated in patterns that give rise to geometry and gravity, Ahmed Almhiri, Shidong, and Daniel Harlow showed in 2014 that the AD-CFT correspondence has the structure of a quantum error correcting code. The bulk physics is protected, in a precise sense, against local errors on the boundary. This explains why the interior of a black hole seems local, why it has the causal structure we expect, even though all its information is encoded non-locally on the horizon. The universe, it seems, has built-in error correction. Reality is robust because it is redundantly encoded. This is why physics is consistent, why experiments are reproducible, why the world makes sense. The holographic encoding has the mathematical structure of a code designed to preserve information against noise. And perhaps that is no accident. We should say something about string theory, because the holographic principle is intimately connected to it, and because string theory provides the mathematical framework within which holography has been most rigorously developed. String theory proposes that the fundamental constituents of matter are not point particles, but tiny, vibrating strings of energy. Different vibration patterns correspond to different particles: electrons, quarks, photons, gravitons. The theory naturally includes gravity, unlike the standard model of particle physics, which describes the other forces but not gravitation. String theory requires extra dimensions, typically 10 spacetime dimensions, compared to the 4 we observe. These extra dimensions are usually assumed to be compactified, curled up so tightly that we cannot detect them. The precise way they are compactified determines the physics of the resulting 4-dimensional universe. The AD-CFT correspondence is a result within string theory. It tells us that string theory on certain curved spacetimes is exactly equivalent to certain quantum field theories on lower dimensional boundaries. This is not an approximation or a conjecture at the level of rigor where it has been checked. It is an exact mathematical equivalence, verified in countless calculations over 2 decades. This means string theory is holographic. Whatever final form a complete theory of quantum gravity takes, if it is related to string theory, it will have holographic structure. The bulk will be equivalent to a boundary. Gravity will emerge from non-gravitational physics. Information will be bounded by area. Not all physicists accept that string theory is the correct theory of nature. It has not made distinctive predictions that have been tested experimentally, and some argue it has become too disconnected from observable physics. These debates continue. But even skeptics of string theory often accept that the holographic principle captures something true about quantum gravity. The arguments for holography, based on black hole entropy, on general principles of quantum mechanics, on the logic of the Bekenstein bound, are broader than string theory. They suggest that any consistent theory of quantum gravity will be holographic, whether or not it is string theory specifically. The holographic principle may be more fundamental than any particular theory. There is a conceptual revolution here that we should make explicit. For most of the 20th century, physics made progress by going smaller. We discovered atoms, then nuclei, then protons and neutrons, then quarks and leptons. Each layer of reality was more fundamental than the last, existing at smaller scales, with larger structures built up from smaller components. The holographic principle inverts this logic. The most fundamental description is not at the smallest scale, but at the boundary, which in many cases is at the largest scale. the edge of the observable universe. The interior, including all the small-scale physics of particles and forces, is emergent, derived, secondary. This does not mean that particle physics is wrong or that the standard model should be discarded. It means that the standard model, general relativity, and all the physics we have discovered are approximate descriptions valid in certain regimes. They emerge from more fundamental holographic physics, just as thermodynamics emerges from statistical mechanics or fluid dynamics emerges from molecular physics. The reductionist program, explaining complex phenomena in terms of simpler components, remains valid. But holography suggests that the endpoint of reduction is not smaller and smaller particles, but something altogether different: information on a boundary, from which particles, forces, and spacetime itself emerge. This is a profound shift in perspective. The fundamental laws of nature, in the holographic view, are not laws governing matter in space. They are laws governing information on surfaces. The physics of the bulk, the physics we observe, is a consequence, a projection, an emergent description. What seemed like the most obvious feature of reality, that we live in a three-dimensional volume, that space extends in three independent directions, that objects have length, width, and depth, may be an emergent approximation to a more fundamental two-dimensional reality. Standing back, what can we say about the holographic principle as a whole? First, it is real physics, not metaphor. The mathematics is rigorous, the predictions are specific, and the framework has withstood decades of scrutiny by the world's best physicists. It may not be the final answer, but it is not speculation either. Second, it changes our understanding of space. Volume is not fundamental. Depth is emergent. The three-dimensional world we experience is real, but it has a two-dimensional description that is equally valid and perhaps more fundamental. Reality has fewer dimensions at its core than we thought. Third, it changes our understanding of information. Information is physical. It cannot be created or destroyed. It is conserved, bounded, and encoded in the structure of space-time itself. The universe is not made of matter plus information. Matter is information. Particles, fields, forces, all are patterns in the cosmic data. Fourth, it offers hope for quantum gravity. The search for a theory uniting quantum mechanics and general relativity has lasted a century. The holographic principle suggests that such a theory exists and has a specific structure. Gravitational physics in the bulk is equivalent to non-gravitational quantum physics on the boundary. We may not have the final theory yet, but we know what it looks like. Fifth, it raises deep philosophical questions. What is reality if depth is constructed? What are we if we are patterns of information? What does it mean to exist in a universe that might be equivalent to data on a distant surface? These questions do not have scientific answers, but science has made them sharper and more urgent. The history of physics is a history of revolutions in our understanding of space, time, and matter. Newton gave us absolute space and absolute time, a fixed stage on which matter moved according to deterministic laws. This picture worked brilliantly for 2 centuries, explaining everything from falling apples to orbiting planets. Einstein shattered it. Special relativity revealed that space and time are not absolute, but relative, intertwined into a 4-dimensional space-time that different observers slice up differently. General relativity went further. Space-time is not a fixed stage, but a dynamic player, curved by matter, telling matter how to move. Gravity is not a force, but geometry. Quantum mechanics brought its own revolution. Matter is not made of little billiard balls following definite paths. It is made of probability waves, superpositions, entangled states. The act of observation plays a fundamental role. Reality at the quantum level is stranger than any classical intuition. And now, perhaps, we are on the verge of another revolution, one that combines quantum mechanics and gravity in a way that transforms our understanding of both. The holographic principle suggests that space-time itself is not fundamental. It is emergent, constructed, derived from something more basic, quantum information on a lower dimensional surface. The three dimensions we move through are not primitive features of reality, but collective approximations emerging from entanglement patterns on a cosmic boundary. If this is true, it would be the most radical shift in physics since quantum mechanics itself. It would mean that the arena of physics, the space-time in which events occur, is itself a physical phenomenon, requiring explanation and subject to laws. The question, what is space, would have an answer beyond mere geometry. Space is the projection of quantum correlations from a holographic surface. We do not yet have the complete theory. The mathematics of de Sitter holography, holography for universes like ours with positive cosmological constant, remains incomplete. The precise mechanism by which three dimensions emerge from two is still being worked out, but the direction of progress is clear and the theoretical evidence is strong. The 21st century may see the completion of this revolution, or it may see the discovery that the universe has even stranger structure than we now imagine. Physics has surprised us before, and it will surprise us again. What we can say with confidence is this: the holographic principle is one of the deepest ideas in modern physics, supported by rigorous mathematics and solving long-standing puzzles. It may not be the final answer, but it is on the path to the final answer. And wherever that path leads, it will change forever how we understand the cosmos and our place within it. We began with a credit card hologram, a shimmering rainbow dove encoded on a flat surface. We end with the possibility that the entire cosmos works the same way. Not a dove, but everything. Not a few inches of embossed plastic, but 46.5 billion light-years of space and time. Not a pretty trick, but the fundamental nature of reality. The holographic principle tells us that we might be living on the surface of a black hole, or rather, that any boundary suffices. Any surface can encode its interior. Any two-dimensional page can contain a three-dimensional story. The boundary of the observable universe holds everything within it. The event horizon of a black hole holds everything that fell in. Surfaces contain volumes. Lower dimensions encode higher ones. This relationship between boundary and bulk, between surface and volume, between lower and higher dimensions, runs through all of modern physics. It appears in black hole thermodynamics, in string theory, in quantum error correction, in quantum computing. Everywhere physicists look, they find the same pattern. Information bounded by area, depth emerging from flatness, the higher encoded in the lower. Some physicists believe this is not just a curious pattern, but a fundamental principle of nature. They believe that any consistent theory of quantum gravity, any theory that successfully unifies quantum mechanics with Einstein's general relativity, must be holographic. The holographic principle is not one possibility among many. It is a requirement, a constraint that any successful theory must satisfy. If this is true, then holography is not just an interesting idea, but a guiding principle for the construction of quantum gravity. It tells us what the theory must look like, even if we do not yet have the full details. It is like knowing that any successful theory of atoms must explain chemical periodicity, or that any successful theory of motion must reduce to Newton's laws in the appropriate limit. The constraint shapes the search. The search continues. Physicists around the world are working on extensions of the AD-CFT correspondence, on holography for de Sitter space, on the emergence of spacetime from entanglement, on the application of quantum error correction to gravitational physics. The holographic principle is no longer a speculative idea on the fringe. It is mainstream physics, studied in the best universities, published in the most prestigious journals, taught to graduate students as part of the standard curriculum. We do not know how the story ends. Perhaps future generations will prove that the universe is definitively holographic, finding experimental evidence that puts the matter beyond doubt. Perhaps they will discover that holography is only part of a larger truth, a stepping stone to an even deeper understanding. Perhaps they will find that our universe has a structure we cannot yet imagine, beyond holography and beyond any framework we currently possess. What we can say is that the holographic principle has earned its place in the history of physics. It has solved problems that resisted solution for decades. It has unified ideas that seemed unrelated. It has opened new doors and pointed new directions. It has changed how we think about space, time, information, and existence. You are here, reading these words, thinking these thoughts, experiencing depth and distance and time. All of this is real. All of this is physics. And all of this might be a hologram. Not in the sense of an illusion, not in the sense of a simulation, but in the sense of an encoding, a pattern, a structure that has equivalent descriptions at different levels of complexity. The universe is what it is, and one of the things it is holographic. We cannot yet prove this for our specific universe. We cannot yet point to an experiment and say, here is the evidence, here is the boundary, here is the encoding made manifest. The mathematics works, the analogies hold, the calculations converge, but the final confirmation remains elusive. Perhaps future experiments will find holographic noise in gravitational wave detectors. Perhaps observations of black hole mergers will reveal new details about horizon entropy. Perhaps a theory of de Sitter holography will emerge and make precise predictions we can test. Physics is patient, and nature eventually answers questions asked clearly enough. In the meantime, we are left with a remarkable possibility that everything we see, everything we are, everything that has ever happened or will ever happen is information. Bits on a boundary, data on a surface, a hologram of extraordinary complexity and beauty, projecting the world we inhabit from a reality we cannot directly perceive. There is one final thought experiment worth considering, because it crystallizes what the holographic principle means for our place in the cosmos. Imagine you could travel to the edge of the observable universe, to the cosmological horizon, 46.5 billion light-years away. What would you find there? Not a wall, not a barrier, not a physical surface. The horizon is not a place in space. It is the limit of what light has had time to reach since the Big Bang. If you traveled there, the horizon would recede ahead of you. You would find more space, more galaxies, more stars, the universe continuing in all directions. And yet, from your original position, the horizon has a definite location. It is a sphere surrounding you, and that sphere has an area, approximately 10 to the 122nd Planck areas. According to the holographic principle, this area bounds the information content of everything inside, everything you have ever seen or will ever see, everything that can affect you or be affected by you is encoded on that distant surface. But here is the strange part. The same is true for every other observer in the universe. Each person, each planet, each galaxy has its own cosmological horizon, its own bounding surface, its own holographic encoding. These horizons overlap and interpenetrate. The information that describes you is encoded on my horizon, and the information that describes me is encoded on yours. We are all, in some sense, holograms of each other. This is not mysticism. It is a consequence of the physics. If information is bounded by area, and if cosmological horizons define the boundaries of causally connected regions, then the information content of the observable universe is encoded on the cosmological horizon as seen from any point within it. Different observers see different horizons, but all horizons encode equivalent information, just from different perspectives. The universe is not a collection of separate things in a container of space. It is a web of information encoded on overlapping surfaces, projecting overlapping bulks. We are patterns in this web, localized disturbances in the cosmic data, temporary arrangements of bits that persist for a while before dissolving back into the noise. This vision is both humbling and exalting. Humbling because it reveals that our sense of solid, three-dimensional existence is an approximation, a convenient way of describing something more abstract and strange. Exalting because it reveals that we are woven into the fabric of reality at the deepest level, patterns in the same data structure that encodes the stars and the void between them. The three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, may be a hologram, an image of reality coded on a distant two-dimensional surface. And you, standing in that hologram, looking out at the stars, wondering what it all means, you are part of the pattern. Information become conscious, data learning to ask questions about itself. That is what the holographic principle says, and it might just be true.